So I would like to do a few connected examples. Let me just start with a typical one-dimensional problem, one that you've done over and over again now, and ask if I drop my physics book from the top of a 30-meter tall building, so let's say the building is 30 meters tall, and I drop my physics book from rest, right, V0 equals 0, how long does it take to get to the ground? So you know how to set up this problem. We don't need to go through all the setup. So I've drawn my picture, I've drawn the direction of all the quantities. I chose plus y as the downward direction, so the displacement is plus 30 meters in the downward direction. We don't put the plus there, sorry. So my displacement is plus 30 meters. My acceleration is plus 9.8 meters per second squared. My time, which is the thing I'm looking for, is unknown. My v initial is equal to 0, and my v final, what's v final? It's unknown, and we actually will not care about it. It is not 0 because we're talking about while it's undergoing constant acceleration. We don't care about what happens after it hits the ground. Okay. So we've done this kind of problem before, which is why I'm rushing through it. So therefore, we can go ahead and just write down all our kinematic equations and then just figure out which one we want to use in order to find t. Since we don't know v, we don't want to use the second one, and we probably want to use the first one. And I'm just going to plug in plus 30 meters equals 1/2 times 9.8 meters per second squared times t squared plus 0 times t, and ignore that mark. So therefore, t is equal to 2.47 seconds. Okay, so now let's throw the book, so we're moving in 2 dimensions. Example 2. So if I throw the book horizontally off the top of the building, meaning the initial velocity is in that direction, V0 equals 5 meters per second. Let's define some directions. Let's call this the plus x direction. Let's call down the plus y direction still, so that the initial velocity is in the plus x direction. And I'm asking how long does it take to get to the ground if delta y is still 30 meters in the downward direction. So now, how do we do? So what's the answer to this problem? So the first thing is you should have gotten the concept by now that the answer is 2.47 seconds, because what happens in the horizontal direction is independent of the fact that it's falling with an initial velocity in the vertical direction of 0, because I've thrown it only horizontally. So it still takes delta t, right, the same amount of time, because we can just treat delta y separate from delta x. So the answer is 2.47 seconds. So what's different in example 2 from example 1? What's different is where the book lands. In example 1, the book is going to land here. In example 2, the book is going to land over here. I didn't mean to draw it right near the x-axis, but you get that. The book is going to land in a different place. So the part B, make part A how long it takes to get to the ground. And again, how do I know it's 2.47 seconds? Well, I can go ahead and just solve it this way. I can say, oh, let's just solve for the motion in the y direction. We can solve for the motion in the y direction separate from the motion in the x direction. But part B is, where does the book land? So now, if I had asked that for example 1, where does the book land? You say the book lands on the ground. The book lands, but where? Where does the book land? The book lands 30 meters down from its initial position and 0 meters across from its initial position, or it lands at the foot of the building, right? So if I want to answer the question in this second part about where does the book land, we are going to be talking about, oh, it goes 30 meters down, but it also goes across some distance delta x away from the foot of the building. So how do we do that? Well, in the y direction, we had delta y equals 1/2 at squared plus v0t, v equals v0 plus at, v squared equals v0 squared plus 2a delta y. What about in the x direction? Well, now we got to be careful. I'm going to be careful. And we've done this before, but I was purposefully not careful in example 1. In the y direction, we've got to just take into account motion in the y direction. So that's That's acceleration in the y direction, velocity in the y direction, initial velocity in the y direction. etc. All of these things need to have a y subscript, right? So what I'm saying is, like with the first equation, the displacement in the y direction is dependent on the acceleration in the y direction. It doesn't matter what the acceleration is in the x direction. The displacement in the y direction is dependent on the initial velocity in the y direction. It doesn't matter what the initial velocity is in the x direction. That's the independence of motion in two dimensions, in two perpendicular directions. Independence of motion in two perpendicular directions means that the displacement in the y direction is dependent only on the acceleration and initial velocity in the y direction. The velocity in the y direction is dependent only on the initial velocity and the acceleration in the y direction, etc. But you might say, oh, but what about time? Is that in the y direction or x direction? Time is time. Time doesn't have a direction. So that's the thing that connects the x equations to the y equations, right? X is independent of y, but in both cases, if it's the same object, time is the same. So that's what connects the x equations to the y equations. So I'll come back to this example too, but let me say in general, we now have, instead of 3 equations, we've got 6 equations. So for two-dimensional motion, instead of 3 equations for one-dimensional motion, we've got 6 equations for two-dimensional motion. What about for three-dimensional motion, right? How many equations do we have if we have to take into account direction to the side, right? In the z direction, right? We're going to have 9 equations. You might think that sounds like a lot, but right, they're reasonably easy algebraically to manipulate. And so, if you've got 9 equations, you got to know a lot of variables to solve them. If you've got 6 equations, you got to know a lot of the variables to solve them. In order to solve these, it might look like a lot, but right, we can solve these 6 equations for every two-dimensional problem. And what I mean by solve is you might be asked for a certain quantity and you might be given other quantities, right? So you might know some quantities and you might not know some quantities, and you're going to solve. So 3 equations, and we actually had figured out, I don't know if you remember, that you needed to know 3 variables in order to solve. I think maybe it was 4. I can't even remember, but we had to know a certain number of variables in order to them to be solvable. 6 equations, you got to know twice as many variables in order for them to be solvable. You got to know twice as many of what the values are of the variables before we can solve for the unknowns. And then with 9 equations, it's going to be 3 times as many. But so that's two-dimensional motion, right? We've just got the equations in the y direction, and you got the equations in the x direction. 3-dimensional motion, we also have the equations in the z direction. Z equations, I won't bother writing them down. You can write the same 3 equations with z subscripts. That says z equations. Okay, so there are 3 of those. Delta z equals, it looks like a 2. 1/2 a sub z t squared plus ... Okay. This is how we do two-dimensional motion. Now, what we're going to start with in this chapter is projectile motion. What is projectile motion? Projectile motion is like the free fall motion that we're talking about in one-dimensional, which is where the object is undergoing acceleration only due to gravity. Only due to gravity. That's a special case of two-dimensional motion, projectile motion.
And we will come back to that concept and finish our example problem next time.